Okay, the last topic of this chapter, also the last topic of E&M, is also one of the most important. This is so-called electromagnetic wave spectrum. You know, all electromagnetic waves in vacuum travel at exactly the same speed, which is the speed of light, c. Okay, yet they can come at totally different frequencies. When we take all kinds of frequencies, all kinds of wavelengths, we put them in the same chart, we have a whole electromagnetic wave spectrum. It is very important for each one of us to have a good idea about different parts of this wave spectrum. Here, in this direction, the frequency goes up, and conversely, over there, the wavelength goes up in the opposite sense, because f and the frequency and the wavelengths are inversely proportional to each other. Okay, f times lambda equals a constant c, which is the speed of light. So we can start with very low frequency or very long wavelengths. Okay, very long wavelengths, then going up directly to medium frequency and medium wavelengths until we reach very high frequency and very short wavelengths. Okay, the general rule of thumb is as we go up, the wave gets stronger. Okay, the individual packages, or we call it photons of the wave, gets more and more energetic. Okay, that is why UV light, which has a lower frequency, a shorter wavelength or higher frequency than visible light, can damage your skin, and X-ray and gamma rays are even more energetic. They're even worse. The X-ray can penetrate the body, and gamma ray can do even more damage. Okay, different parts of the electromagnetic wave spectrum have different characteristics with different applications, even though they all travel at the same speed. We should have some general idea how each part of the electromagnetic wave play a role. Okay, we start from the very low end of the frequency or very long wavelengths. We call it radio wave. Okay, radio waves, for example, we can use them for radio broadcasts. That's why we call them radio waves. Okay, the wavelength of the radio wave can go up from extremely long, which is thousands of miles or even longer, to about a meter or so. Okay, to about a meter or so. So it's a very, very large range. So about a meter. And the frequency can go from very, very low to about 10 to the 8 hertz, roughly. Okay, you got to understand that as we go from radio wave to the next one, which is microwave, there is no exact cutoff where microwave begins and radio wave ends. Okay, it's a continuous spectrum. All right, and some notable radio waves, AM and FM. These are radio waves we use to receive radio signals, right? FM and AM, what do they mean? Well, AM means frequency, means amplitude modulation. The typical carrying frequency is about 1 megahertz or 10 to the 6 hertz. Okay, the typical wavelengths for AM wave, it's as you can see here, 1 megahertz is 10 to the 6. So the wavelength is about several hundred meters. Okay, several hundred meters. This type of wavelength is so long that it can go around, the signal can go around buildings, easily can go around buildings. And this is why an AM station, the tower does not have to be very high. You don't have to be at the line of sight. Okay, signal can easily pass, can negotiate, city blocks and buildings, that sort of thing. FM is frequency modulation. So you boost the frequency, the carry frequency to about 100 megahertz or so. Okay, and what they do is each station will vary their frequency output slightly around a central broadcasting frequency, and the varying frequency is the way they carry the broadcasting signal. Unlike AM, is the varying amplitude that carries the signal. So you can see FM frequencies are about 100 times higher than AM, so the information is denser, and therefore the broadcasting quality is higher. Okay, now you go up from radio wave. Next, you will get microwave. Okay, microwave. What comes into mind when you talk about microwave? Well, microwave oven, right? Microwaves have frequencies higher than radio wave, and as far as the wavelengths, they can go, to around centimeter millimeter mark. Okay, centimeter millimeter mark, so a millimeter or so. Again, there's no exact cutoff. Okay, the reason why microwaves can be used as to build microwave oven is because microwaves will cause water molecules to resonate. So water can easily absorb energy from the microwave, and so that's how you heat up the food, because of the water content of the food. Also, since microwaves have higher frequency than radio waves, they carry signal at a denser rate, and therefore they can be used for television broadcasting, which requires a visual signal instead of just an audio signal for radios. And going up from that, you will get into infrared. Okay, what does infrared mean? Infra means lower in frequency than. Okay, so infrared means what? The frequency of the signal is lower than that of red light. Okay, now red light has the longest wavelengths of any visible light, right? So infrared is something we cannot see, but infrared is still very useful because infrared can be used to carry signals. Okay, infrared is also the dominant radiation produced by any object whose surface temperature is around room temperature. Okay, so anything that we see around us, like a desk, a book, a table, a building, even you and I, okay, we all have surface temperatures around room temperature. Therefore, we radiate electromagnetic wave and we absorb electromagnetic primarily in the infrared range. Okay, it gives us warmth, right? Gives us warmth. So when you're near a person, you feel the warmth, and that is because of the infrared radiation coming out from that person. Infrared can also be used to transmit satellite signals. For example, satellite TVs require infrared signal. As you go higher and higher, okay, this by the way, infrared goes to about 1 micron also, about half a micron to 1 micron. That's the higher limit, a lower limit for the wavelengths. As you go to a very low, very short wavelengths and very high frequency, then when a wave at such a short wavelength will try to get around an obstacle, it cannot get around an obstacle that is much bigger inside than its wavelengths. And since these wavelengths are so short, basically, when you get infrared or higher frequency, these signals cannot easily go through, get around, a microscopic sized objects such as a person, such as a book, or such even tea leaves. Okay, so therefore, if you want to broadcast something with infrared signal, you would require line of sight. Okay, for example, satellite TVs, the broadcasting source is a satellite. Okay, and if you have a satellite dish aimed at that satellite, you want to make sure the dish points directly towards the satellite with nothing in between. There is no obstacle. You cannot have an obstacle. It must be in a line of sight, facing clear sky. Okay. Now above that, there is a very narrow band, but extremely important. What is that? That, of course, is visible light. Okay. Visible light. Visible light has a typical frequency of 10 to the 14 hertz, very, very high, and it's got a typical wavelength about half a micron. Keep that in mind. Okay, about half a micron. This is very short compared with microscopic size, such as a person. Okay, and therefore, visible light, as you know clearly, can only travel along the so-called line of sight. Okay, it does not bend around closed doors, for example. Unlike sound, you can actually hear a person behind doors, but you can see that person behind doors. That is because sound waves, audible sound waves, have typical wavelengths of the size of the door itself, so therefore it can go around the door, and yet visible light cannot. Okay, the wavelength is too short. All right, going above that, we have ultraviolet, UV. The photons of ultraviolet light is more energetic than the photons of visible light, so they can penetrate our skin, they can cause damage, and that is a general rule. In fact, if you go even higher to X-ray and gamma ray, things will get even worse. Okay, UV light has its positive and minus sides. For example, you can also use UV light to your advantage. For example, you use that as a way to kill germs. Okay, because of their high energy. Now, above UV, you have what's called X-ray, and then above that you have gamma rays. Okay, X-rays are typically generated when a high-speed beam of electrons hit a piece of metal. Or you can also be generated from medium to large size atoms. Okay, when an atom, you can see, you will learn from physics 1D, when there is a vacancy near the bottom of the energy band, of the energy levels of a medium to large size atom, then an outside electron will come to fill the void, and the energy lost by that electron will then be given off in terms of X-rays. A typical X-ray photon will have wavelengths only about the size of a nanometer, okay? A nanometer, which is even shorter than visible light, and the energy is even higher. And of all the electromagnetic magnetic rays, the greatest energy carrier is the gamma ray. Okay, gamma rays are typically produced when atomic nucleus undergoes a transition from a higher to a lower energy state, and the energy carried by the gamma ray can be tremendous. Therefore, gamma rays are dangerous. Okay, you need to protect yourself from gamma rays. But on the other hand, you can also direct gamma rays with specific directions to destroy brain tumors, and this is something you might have heard. It's called gamma knife. Now, there are so many stories about every part of the electromagnetic wave spectrum. Okay, what I want you to do is to not just listen to this, but go back to the textbook and read the section of electromagnetic wave spectrum very carefully. Make sure you are familiar with, what each band of the electromagnetic wave is capable of doing, and get familiar with roughly the cutoff wavelengths and cutoff frequencies of the electromagnetic wave. Okay, and many of you will find a career in, say, telecom industry, electronic engineering, optical engineering, that sort of thing. So essentially what you'll be doing is that you're going to make a living off of a certain frequency range of the electromagnetic wave. For example, if you are working on optical devices which carries a land-based signal, okay, for internet connection, for ultra high-speed internet connection, then you're typically using visible light. On the other hand, if you do wireless transmission, then you cannot use visible light. It doesn't go very far because of the scattering of the air molecules. The visible light can never go very, very far, and therefore you have to go with a lower frequency, which is infrared, or even lower frequency. Okay, you can go to microwave. That actually are cell phones. A cell phone's signals are carried in the microwave range. Okay, so again, you'll be employing different parts of the electromagnetic wave for that purpose. So therefore, it is very important for every one of us to get familiarized with this electromagnetic spectrum chart. And in the textbook, there is a much better chart than the one I drew here. So please make sure you take a good look at it.